Welcome to the RBFS Fundamentals Training Series. In this video, we will cover Part 2 of Subscriber Management Theory and Configuration, focusing on IP over Ethernet. We already looked at IPoE in Part 1. However, since most of you use either IPoE or IPoE, but not both, we will repeat a few things in this clip. If you have already watched Part 1, you can simply skip the first section. The configuration examples and demos in this video are based on RBFS version 24.9.1. Before we dive into the basics of the IPoE protocol and its implementation in RBFS, a brief disclaimer. This clip is free to use for non-commercial purposes and is designed to help you become familiar with RBFS through self-study. However, please note that it does not cover all configuration options available in RBFS, and implementation may change in future versions. Let's have a brief overview of what we'll cover in this video. We will start with a brief introduction to broadband access networks to outline the basic architecture and clarify some key terms. Next, we'll take a closer look at how IPoE works, explaining the steps to establish and manage DHCP sessions. Afterwards, we'll put the theory into practice, guiding you through the necessary steps to implement IPoE subscriber management in RBFS, covering both IPv4 and IPv6 configurations. We will then present some useful commands to monitor IPoE subscriber activities, which will also help us troubleshooting. Finally, we'll dive into Radius services and explain how Radius can simplify subscriber management. We'll cover both the theory and practical implementation of Radius. Let's jump into a brief overview of subscriber management. A broadband access network is used to connect customer locations, either business or residential, to a service provider. We will follow the terminology used in TR 101, as defined by the Broadband Forum, which describes Ethernet-centric broadband access. At the customer location, the customer premise equipment, CPE, terminates the local loop, providing the interface between the customer's devices and the network. The CPE is sometimes called a routing gateway or home gateway, but for this presentation, we will stick to CPE. Depending on the access technology on the local loop, the CPE can be physically connected to a variety of different devices. With fiber to the home, fiber cables are installed all the way to the customer premise. The fiber is attached to an optical network termination device, which is responsible for translating optical into electrical signals and is connected to the CPE. The remote end of the fiber is connected to an optical line termination device, which aggregates multiple users. Fiber to the building access is very similar to fiber to the home, but instead of a separate fiber to each apartment, there is a single fiber to the building terminating at an distribution point unit. Standard copper cables are then used to connect the DPU with the CPEs within the building. If a flavor of digital subscriber line, XDSL, is implemented, the CPE usually has a DSL modem integrated and is physically connected to a multi-service access node, MSAN, which aggregates multiple subscribers. In the past, this system was called a DSL access multiplexer, DSLAM. The fiber-to-the-curb approach is similar to the XDSL. The main difference is that the MSANs are smaller and located closer to the customer. In case of cable access, the CPE has a built-in cable modem which is connected to a cable modem termination system, CMTS, using coaxial cables. Again, the CMTS aggregates multiple subscribers. The aggregation devices, for example OLT or MSAN, are connected to the Ethernet aggregation network, which then connects to the broadband network gateway. Our main focus in this presentation will be the broadband network gateway, short BNG. Historically, the BNG was known as a broadband remote access server or BRAS, but we will use the term BNG throughout this presentation. At the BNG, customers typically refer to subscribers or users. The BNG acts as a router that forwards packets between the core network and the customer location providing internet access. To interconnect with the core network, the BNG must support IP routing protocols such as BGP, OSPF, or ISAS. The BNG typically supports MPLS to provide services like Layer 2 and Layer 3 VPNs, along with traffic engineering and fast reroute capabilities. If services such as IPTV are offered, protocols for IP multicast group management and traffic replication may be implemented. While traditional routers focus on these routing features, the BNG also handles key functions necessary for managing broadband users. Most importantly, the BNG is responsible for managing subscriber sessions, which includes user authentication, session establishment, and session termination. One aspect of session management is session accounting to create billing information. In this context, a subscriber session can either be an IPoE or a PPPoE session. In this presentation we will focus on IPoE. Once the session is successfully established, the BNG assigns IP addresses to customers, enabling internet connectivity. IP addresses can be allocated from locally defined pools, DHCP servers, or radius servers. Traffic management includes functions like quality of service to prioritize certain types of traffic, ensuring optimal user experience for applications like video streaming or gaming. It also includes traffic rate limiting. The BNG also plays an important role in applying security policies to protect the network. In broadband access networks, the BNG is a critical component, particularly because it needs to support large-scale deployments, with thousands or even tens of thousands of users. As such, scalability and reliability are essential to ensure that the network can handle the high volume of concurrent connections and traffic. Independent of the access technology, an important aspect of the network design is the logical structure of the Ethernet aggregation network. Basically, there are two different VLAN models that can be used. The one-to-one VLAN model and the N-to-one VLAN model. In the one-to-one VLAN model, each subscriber is assigned a unique customer VLAN, or CVLAN, which carries all the traffic for this customer. This provides a direct one-to-one mapping between VLANs and subscribers. New services can be added easily without affecting others. The one-to-one model is recommended because it simplifies operations and offers flexibility for features like backhauling, bitstream access, and QoS. The VLAN ID is a 12-bit unsigned integer, which limits the number of VLANs and thus the number of customers to 4096. In order to increase the scaling, double-stacked VLANs can be introduced. In most cases, the outer VLAN represents the aggregation device. The shared N-to-one VLAN model offers many-to-one subscriber-to-service connectivity, where multiple subscribers share a single service VLAN, or SVLAN. Usually, there are separate SVLANs for internet connectivity, IP telephony and IPTV. Access protocols can provide features such as automatic IP addressing, and enable a framework for authorization and authentication into service provider networks. There are two common access protocols used, IP over Ethernet, and PPP over Ethernet. PPPoE is covered in another clip. In this section, we will explain how exactly IPoE works. Internet Protocol over Ethernet, short IPoE, is a method of delivering IP packets directly over an Ethernet network without the need for additional encapsulation, which reduces packet overhead. The outermost layer is the standard Ethernet frame, which includes the destination MAC address, source MAC address, and ether type. Optionally, one or two additional VLAN headers can be inserted. Inside the Ethernet frame, you have a standard IP packet. With IPoE, there is no need to establish, maintain, or tear down a dedicated subscriber session. Devices simply send and receive IP packets over Ethernet, and subscribers are identified by their MAC addresses. Subscribers are commonly assigned an IP address dynamically, typically via the Dynamic Host Configuration Protocol, DHCP, for IPv4 or DHCPv6 for IPv6. However, it is also possible to statically assign IP addresses. RBFS supports the configuration of a local DHCP server as well as a method to relay DHCP requests to an external server. The creation of a subscriber state is triggered by DHCP messages. A disadvantage of IPoE is the lack of a built-in mechanism for authentication, as there are no protocols like CHAP or PAP available to facilitate the exchange of credentials. It is possible to authenticate IPoE subscribers based on their MAC addresses, however, this method may fail if CPE routers are replaced. Additionally, IPoE does not provide keep-alive methods, thus offering no control over the operation of the connection. As DHCP is a critical component of IPoE, let's take a closer look at how IPv4 address assignment works step by step. DHCP is a client-server protocol. The DHCP client is a software component that resides within modern CPE devices. The client initiates the exchange of protocol messages by sending a DHCP discover message to the server. This message is a broadcast message both on Layer 2 and Layer 3 in order to seek a DHCP server that can assign an IP address. DHCP uses UDP as a transport protocol. Messages from a client to a server are sent to port 67, while messages from a server to a client are sent to port 68. Once the DHCP server receives the DHCP discover message, it responds with a DHCP offer message. This message contains an IPv4 address that is not currently in use and that is encoded in the Your IP address field, as well as a subnet mask, and the lease time. In addition, optional parameters such as the default gateway or DNS servers may be included. The server encodes its own IP address in the Server IP address field. The DHCP offer is sent back to the client device as a unicast using a temporary IPv4 address. Depending on the number of DHCP servers in the network, the client receives one or more DHCP offer messages which it can choose from. The client sends a DHCP request message back to the server. This message is a broadcast message to inform all servers about which offer was accepted, so that other servers do not assign the same IP address. The DHCP request message must contain the server identifier field set to the DHCP server address to ensure that the chosen server can identify itself as accepted. The message must also define the requested IP address field, which is set to the Your IP address value from the original offer message. When the DHCP server receives the DHCP request, it verifies that the offered IP address is still available. It sends a DHCP acknowledge message to the client. This message confirms that the IP address has been assigned, along with any other configuration details, like subnet mask, default gateway, etc. Any configuration parameters in the acknowledge message should not conflict with those in the earlier offer message accepted by the client. The assigned IP address is valid for a specific period, called the lease time. Before the lease time expires, the client device can request to renew the lease for the same IP address by sending a DHCP request to the server. If the server approves the renewal, it will send a DHCP acknowledgement with a new lease time. If the client does not renew the lease, the IP address is returned to the DHCP server's pool to be assigned to another device. In case the subscriber wants to disconnect, it can send a DHCP release message to the server returning the IP address before the lease time expires. Instead of providing DHCP server functionality directly on the BNG, an external DHCP server can be used. In this case, the BNG acts as a relay, forwarding DHCP messages between the client and the server. This feature is known as the DHCP relay agent. We will not delve into the specifics of the DHCP message flow, as it remains largely the same from the client's perspective. The relay agent forwards all broadcast packets received from the client to the DHCP server. Since the DHCP server is no longer directly connected, the communication occurs via IP unicast. The relay agent identifies itself by using the gateway IP address field. On the return side, the DHCP relay agent forwards all messages received from the server to the client, once again setting the gateway IP address field to its own IP address. To add support for IPv6, address assignment and configuration are managed by DHCP v6. While the core mechanics are similar to DHCP-v4, DHCP-v6 introduces significant changes. For example, DHCP-v6 messages are no longer sent to a broadcast address. Instead, IPv6 uses a special-purpose multicast address that DHCP-v6 servers and relay agents listen to. While UDP remains the transport protocol, the port numbers have changed. Servers and relay agents listen on port 547, while clients listen on port 546. Additionally, DHCP-v6 message names have changed. The discover message in DHCP-v4 is now called the solicit message, the offer message is renamed to advertise, and the acknowledge message is now the reply. In DHCP-v4, the client's MAC address was used for authentication. In DHCP-v6, both clients and servers generate a unique identifier called the DHCP Unique Identifier, DUID, which can be based on the link layer address or an enterprise ID. The DUID is used throughout the process to identify peers. The IPv6 address assigned to a subscriber's CPE device on the WAN link is managed through an attribute called the Identity Association for Non-Temporary Address, INA. In IPv4, a subscriber typically receives a single public IPv4 address and uses network address translation on the CPE device to provide connectivity to LAN devices. One of IPv6's main goals was to eliminate the need for network address translation. Consequently, the BNG assigns multiple IPv6 addresses to the subscriber's devices. This process, known as IPv6 prefix delegation, is also handled by DHCP-v6 using the Identity Association for Prefix Delegation, IAPD, attribute. The Broadband Forum's TR-187 document suggests that service providers delegate an IPv6 prefix of /56 to customers, allowing them to create up to 256 subnets within their network. The DHCP-v6 message flow is similar to DHCP-v4, involving 4 messages exchanged before the client receives the requested information. DHCP-v6 also offers a 2-message communication option called Rapid Commit. When enabled, the server responds directly with a DHCP-v6 reply message, bypassing the advertise and request messages, based on the Rapid Commit option set in the initial solicit message by the client. Now that we are familiar with the concept of IPoE in DHCP, let's move to the implementation in RBFS and see how to configure. Rtbrick's modular and scalable subscriber management, referred to as next-generation access infrastructure, supports a range of access protocols including IPoE and Radius. This system is designed to deliver carrier-grade Internet access services, with a focus on scalability, interoperability, and robustness. By providing support for multiple access protocols, RBFS ensures flexibility in deployment and compatibility with various network configurations, which is crucial for operators looking to provide consistent and high-quality services to their customers. Rtbrick's implementation utilizes a distributed architecture to enhance both scalability and stability. The distributed nature of this architecture allows multiple processes to manage different aspects of subscriber connections concurrently, reducing bottlenecks and ensuring that the system can handle a large number of subscribers efficiently. There are 4 main daemons in the Rtbrick distributed access architecture. The subscriber daemon serves as the central component, managing the current subscriber state and handling authentication, authorization, and accounting. It also serves as the interface to the forwarding infrastructure, responsible to request per subscriber QoS, filters, and more. The PPPoE daemon handles PPPoE and PPP sessions for subscribers including subprotocols as ICMPv6 and DHCP-v6 where the implementation for PPPoE differs compared to IPE. The L2TP daemon is responsible to manage L2TPv2 tunnels and sessions. The IPoE daemon handles protocols related to IPoE subscribers like DHCP-v4 and DHCP-v6. RBFS subscriber management configuration involves setting up various profiles and parameters that control how subscribers interact with network services. This includes authentication, service access, protocol handling, and other functions organized under a structured configuration hierarchy. There are 3 mandatory configuration options in RBFS. The AAA profile ensures that all subscribers are authenticated before accessing services, authorized to use those services, and accounted for billing and monitoring purposes. The access profile defines various parameters to control how RBFS handles network traffic and client interactions. For IPoE, the configuration mainly includes DHCP and DHCPv6 settings as well as activation of IPv4 and IPv6 address families with corresponding settings. Finally, the access interface configuration is the anchor point for almost all further access configurations. The interface configuration defines the physical interface name along with VLAN ranges, as well as the access type, which in our case is IPoE. In addition, the mandatory access profile and the AAA profile are associated with the access interface. Although IP address pool configuration is not mandatory, in absence of other IP address assignment methods, it is a common configuration step. The address pool is linked to the access profile. Keep in mind that all subscriber management configurations and profiles are managed under the top-level hierarchy access. This hierarchy acts as the central point for defining and managing all access-related settings. Enough of theory, let's put this into practice with a simple example. We are using a consolidated BNG image running RBFS 24.9.1.1 in a virtual environment. Currently, there is no access configuration present on the device. We begin with the access profile configuration. This is done via the set access profile command. We need to define a profile name. In this example, the profile name is IPoE_access. As all commands in the RBFS configuration use small letters, I personally prefer to use capital letters for profile names, but you can use any other naming convention. In this access profile, we define the routing instance to be the default instance. We enable the DHCP protocol and set the DHCP mode to server. Finally, we enable the IPv4 address family. Going back to our IPoE configuration building blocks, we have now completed the access profile configuration by enabling DHCP and activating the IPv4 address family. Let's move on to the AAA profile configuration. AAA is short for authentication, authorization, and accounting. The AAA profile is a mandatory configuration step that serves as a cornerstone for managing and tracking subscriber activities. The AAA profile is configured using the set access AAA profile CLI command. We need to define a profile name and an authentication method. In our example, we set the profile name to IPoE_auth. RBFS offers a couple of options for authentication. With the local option, the subscribers are authenticated based on locally defined user profiles. The radius option is used to send authentication requests to a radius server. We will come back to this option later in the presentation. For the sake of simplicity, we bypass the authentication by setting authentication method to none. After completing 2 out of 3 configuration tasks so far, we proceed to configure the access interface. So, let's move on to the access interface configuration. We use the set access interface command hierarchy to define the access interface. Using the question mark again, we see that we now have 3 options: untagged, single-tagged, and double-tagged. In our example, we choose double-tagged, which is the most common one for the one-to-one VLAN model discussed early in this clip. The physical interface, to which our clients are connected to, is hostive 004 and the VLAN range is from 128 to 159 for the outer VLAN, and 1 to 100 for the inner VLAN. The access interface configuration provides some optional settings, for example the maximum number of subscribers per VLAN. We will limit the configuration to the mandatory tasks. We define the access type as IPoE, and we associate the previously defined access profile and AAA profile with it. We also define the gateway IFL, which is used as an unnumbered source interface. Okay, once this is done, we commit the configuration. Now, we switch to a server connected via interface hostif 004 to the RBFS system. This server has an application installed called BNG Blaster. The BNG Blaster is an open-source network tester for routing and access protocols actively maintained and evolved by Rtbrick. For more information about the BNG Blaster, visit the project documentation on GitHub. We will use the BNG Blaster to generate a IPE client session. So, let's start with a predefined configuration file for IPv4 single-stack subscribers, that defines an interface matching the VLAN ranges on the BNG and which enables DHCP client. The BNG Blaster command takes this JSON file as input as well as the number of simulated subscribers, in our case 1. As we can see, the BNG Blaster tries to establish one IPE session but it fails. This is a good starting point for some initial troubleshooting. Switching back to RBFS, let's monitor the subscriber login attempts. We can see that the subscriber periodically tries to connect, but the session is terminated immediately. A very nice feature in RBFS is the Show Subscriber History command, which displays previous logins, successful ones as well as failed ones. We spot that the termination reason is no IP address. The client does not have an IP address, nor does it get one assigned from the BNG. The address pool configuration is not mandatory, but as we do not have defined any other source, which can be used by the local DHCP server to assign an IP address to the subscriber, we will fix this issue by creating an IPv4 address pool. An IPv4 address pool is defined using the setAccessPool command hierarchy. In our example, the pool name is defined as IPoE_pool_IPv4. The command requires to configure the first and the last IPv4 address in the pool. For the client to get internet connectivity, the subscriber IP address needs to be routed to the core network. For stability reason, it is not a good idea to redistribute the assigned IP address one by one into any kind of routing protocol. It's best practice to define a static route for the complete address pool with nexthop set to null. So, we define the nexthop profile first and the static route afterwards. As we are running BGP in the core network, we will redistribute this static route into BGP. After we have created a pool, we need to assign this pool to the address family part of the access profile configuration using the pool name options. And while we are at it, let's add the primary and secondary DNS servers to the access profile as well. After committing this fix, we can restart the BNG Blaster. Now we generate 5 sessions, and see what happens. 5 DHCPv4 sessions are successfully created. Switching back to RBFS CLA, we can verify that there are 5 IPoE sessions active. Let's take a short break to summarize the configuration we've created so far. For a minimal IPoE configuration, we must first create an IPv4 address pool. Secondly, we create an access profile in which DHCP is enabled, and the IPv4 address family is activated and the previously defined address pool is referenced. Thirdly, an AAA profile must be created that, in the simplest case, allows all subscribers. Finally, an access interface is configured on the corresponding physical interface with the associated VLAN range. The access protocol is set to IPoE and both, the access profile and the AAA profile are bound to it. Additional settings such as the maximum number of subscribers per MAC address or per VLAN can be applied to the access interface. Please pause the video if you need more time to review these configuration steps. So far, we have successfully configured IPoE sessions to support IPv4. The process of configuring IPv6 support is very similar to that of IPv4. Instead of using DHCP, the DHCP-v6 is used as the network protocol for IPv6. Next, we enable the IPv6 address family. Similar to IPv4, we configure an IPv6 pool name. As an additional configuration step, we add the prefix delegation pool name. In an IPv4 scenario, the subscriber typically receives a single public IP address and uses network address translation on the CPE device to provide connectivity to other devices in the LAN. However, one of the primary motivations behind the development of IPv6 was to eliminate the need for network address translation. Consequently, the broadband network gateway must assign additional IPv6 addresses to the subscriber's devices. This process is known as IPv6 prefix delegation. We also specify a primary and secondary DNS server. The IPv6 address pools assigned to the access profile are not yet defined. Let's create two pools, one for the WAN link with prefix length of /128 and one for the delegated prefixes. We use the set access pool command again, but this time of type IPv6 prefix. The Broadband Forums TR-187 document, which outlines IPv6 deployment in broadband networks, suggests that service providers delegate an IPv6 prefix of /56 to the customer. This allows the customer to create up to 256 subnets within their network. Finally, we create a static route for each IPv6 address pools and redistribute these static routes into BGP again. In order to demonstrate that this dual-stack configuration is working as expected, we start the BNG Blaster once more, this time, with a dual-stack IPv4 IPv6 configuration and generate 5 session. As we can see, the BNG Blasters shows 5 DHCP-v4 and 5 DHCP-v6 sessions and RBFS CLI also shows 5 active sessions. To summarize, in contrast to IPv4, with IPv6 we need 2 address pools, one for the WAN links and one for the delegated prefix. In addition, the IPv6 address family needs to be activated, and the IPv6 address pools need to be associated. Last but not least, DHCP-v6 protocol is enabled. To conclude the section on configuring IPoE and RBFS, we would like to briefly mention that there are also service profiles. Service profiles can be defined using the set access service profile command and bound to the access interface. Without going into further details, the service profiles offer the possibility of providing subscriber-specific services, such as quality of service, multicast support, network address translation, or subscriber-related access control lists. Now that we have successfully configured IPoE and have also seen that DHCP sessions have been established with the BNG, we would like to demonstrate some more RBFS commands that are helpful for monitoring and troubleshooting subscriber sessions. A BNG can easily terminate thousands or even tens of thousands subscriber sessions. Therefore, a simple show command is not very helpful if you are looking for a specific subscriber. RBFS offers the option of specifying a filter on the CLI that searches for sessions with predefined criteria, for example interface name, VLANs, MAC address, or username. Each subscriber in RBFS is uniquely identified by a 64-bit number called the subscriber ID, which remains unique across all RBFS processes and even across chassis in the context of high availability. Once we have the subscriber's session ID, we can retrieve more information about the session using the detail keyword. For instance, the username and the subscriber's IFL are displayed, which consists of the physical port combined with the session ID. We can also extract the IPv4 and IPv6 information related to this session. We are already familiar with the show subscriber history command. Again, we can use filters to restrict the output. As these are IPoE sessions, we can also use the show IPoE subscriber command to list all subscribers. This command also supports filter options to restrict the output. In combination with the session ID and detail keyword, we can obtain useful information about the DHCP and DHCPv6 status of the session. If local IP address pools are configured, we can monitor them with the show subscriber pool command. The summary option provides a list of all configured IP address pools as well as their usage. It is also possible to view the allocation of IP addresses from a specific pool. An overall statistics of the number of subscribers connected to the BNG can be retrieved using the show subscriber count command. There is a summary as well as a breakdown to all access interfaces. The command output also displays all access types. I have put together the commands that I just showed you into a couple of slides as a reference. The most important takeaway is that we have the show subscriber and the show IPoE subscriber command hierarchies, which display slightly different information. While the show subscriber detail command focuses on layer 3 specific information such as IP addresses, the show IPoE subscriber detail focuses on the DHCP state. The show subscriber history command provides some information on previous logins, which might be useful for troubleshooting. Both commands use the same session IDs and share the ability to filter the output based on customer information such as MAC address, physical interface, or VLAN information. The show subscriber pool command lists all local configured IPv4 and IPv6 address pools and their utilization. Finally, the show subscriber count command provides a summary of all subscriber sessions independent of their type and their breakdown into interfaces. Please pause the video if you need more time to review them. Before we move on to the next section, I want to briefly demonstrate how to configure DHCP relay. We have already seen that instead of configuring a local IP address pool, we can also use an external DHCP server for address assignment. We need to make sure the DHCP server is reachable. In our example, the DHCP server is directly connected to interface hostIF 000 using VLAN 10 and has an IP address of 172.16.101.2. Let's create the interface configuration first and verify reachability. Next, we define the DHCP server using the setAccess DHCP server command. We can choose any name for the server, for example DHCP_server, and specify the IP address of the server and the source address of the BNG for this communication. Finally, we change the DHCP mode in the access profile from server to relay and associate the DHCP server definition we just created with the access profile. In order to verify proper configuration, we switch back to the BNG Blaster and create 5 IPoE sessions. The show subscriber command confirms that we have 5 active sessions on the BNG. Now, let's verify that those sessions really got their IP addresses from an external server. We can inspect the local pool utilization and see that there were no IPv4 addresses taken from pool IPoE_pool_IPv4. If we inspect one of the session in more detail, we recognize that the assigned IP address is 192.168.164.0, which is not part of a local pool. In addition, the DNS servers differ from the ones defined in the access profile. We can conclude that the IP settings have been assigned from an external DHCP server. Once again, I have put together the commands that I just showed you as a reference. If you have multiple BNGs, it does not scale to configure user-specific options on each device because it may cause inconsistencies, especially when migrating users from one BNG to another. The next section deals with Radius, which is a method to simplify operation by providing user-centric configuration and data in a central repository. Remote Authentication Dial-In User Service, short Radius, is a networking protocol that provides centralized authentication, authorization, and accounting, or AAA, for users who connect to a BNG and use a network service. Authentication is the process of validating subscriber identities before allowing them access to the network. Authorization determines what kind of services a user is allowed to use. Accounting tracks user activities, such as the number of packets and bytes transmitted, and the amount of time the session is active. This information can be used for billing and monitoring purposes. Radius is a client-server protocol that uses UDP for communication. IPoE subscribers are connected to a BNG device, which serves as a Radius client. In Radius terminology, the BNG is also called a network access server. Let's dive into the protocol details. When an IPoE subscriber connects to the BNG, it sends a DHCP discover message. In contrast to PPP, DHCP messages do not support any user credentials. However, as the DHCP message contains the source MAC address of the client, this information can be used as an identity to authenticate the subscriber. For each IPoE subscriber, a username is generated automatically using the client's MAC address followed by @IPoE. The password is simply IPoE. Furthermore, other DHCP information such as the circuit ID or remote circuit ID encoded in DHCP option 82 may be used for authentication. Instead of using a local user database, the BNG sends a Radius access request to the Radius server. The access request contains the user information, along with an authenticator ID and the NAS IP address. The Radius server responds with either an access reject or access accept message. The access accept message may contain additional configuration options, such as framed IP address, framed route, DNS server, etc. The BNG continues with the DHCP message exchange, sending a DHCP offer to the client once it receives the access accept from the Radius server. If Radius accounting is enabled, the BNG sends an accounting request of type accounting start to the Radius server, including the username and accounting data once the DHCP message exchange is completed. The Radius server replies with an accounting response packet. When an IPoE client disconnects, either due to timeout or DHCP lease message, the BNG sends an accounting request of type accounting stop to the Radius server, which is acknowledged by an accounting response packet. The accounting stop message contains total data usage in both directions, the number of packets as well as the volume, and the session duration. Since a BNG might crash or the accounting stop message might be lost, Radius provides interim accounting updates, which the BNG can send periodically to avoid the loss of accounting data. Change of authorization is a mechanism that allows dynamic changes to a subscriber's session without needing to tear down and re-establish the session. For instance, a Radius server can send a change of authorization request to the BNG to adjust session parameters like bandwidth changes or activation/deactivation of legal interception. The BNG responds to the change of authorization request with either a change of authorization acknowledge to accept the changes or a change of authorization negative acknowledge message to reject the changes. To improve our understanding of Radius services, and its interaction with the BNG, let us configure Radius on RBFS step by step and complete this section with some monitoring commands. We have seen this diagram in parts before, and we already know that an AAA profile is a mandatory part of the configuration. When configuring Radius, there are two additional building blocks. The first one is the Radius server definition. You can configure multiple Radius servers. The Radius server configuration includes the IP address of the server, the credentials for communication, and whether this server can be used for authentication, accounting, or both. Optionally, you can define the UDP port for authentication and accounting communication. The Radius profile defines which of the previously defined servers should be used for authentication and accounting. Although a particular Radius server might be capable of handling both authentication and accounting, in the Radius profile, you can specify that it should only perform one of these tasks. You can provide a list of servers to allow for redundancy or load balancing. Finally, the Radius profile is linked to the AAA profile. Before we do the Radius configuration itself, let's undo the DHCP relay configuration to avoid conflicts. We must ensure that the Radius servers are reachable in our network. In most cases, the Radius servers are located in a data center and the communication is done in-band via the core network. For sake of simplicity, our Radius server is directly connected to interface host 000 using VLAN 20. Its IP address is 172.16.101.18, so we use the .17 for the interface address. Let's create the interface configuration first and verify reachability. Next, we define a Radius server using the set access Radius server command hierarchy. The Radius server is simply named SN, but you can choose any name. We define the IP address of the server, the source IP address from which we are sending our packets, the routing instance, and the passkey for the Radius communication. Afterwards, we enable authentication and accounting and also define the corresponding UDP ports. The Radius profile is configured using the set access Radius profile command. I use the name my RAD_profile_sample, but again, you can choose any name you like. We define the NAS identifier to be BNG and the NAS IP address. Both of these values might be used by the Radius server to take specific decisions. We also configure the NAS port type to be Ethernet. Next, we add our Radius server to the list of authentication and accounting servers. Our previously defined AAA profile did not use any authentication. So, let's first delete the old profile and create a new one using authentication order set to Radius and accounting order also set to Radius. At this point, we can add accounting parameters such as interim update interval to the configuration. We then link our radius profile to this AAA profile. Let's switch to the BNG Blaster again and generate a couple of IPoE subscriber sessions. On our BNG system, we can verify that 5 IPoE sessions were successfully set up. How can we verify that these sessions were really authenticated by Radius? If we check the IP address pool allocation, we can see that 4 addresses were allocated from each pool. However, we have 5 sessions established. The pool allocation reveals that one of the subscribers did not get an IP address assigned from the pool. Inspecting this subscriber in detail, we see that it got an IP address, which is not part of the local pool definition. We further notice that it has DNS servers assigned that are different from the ones defined in the access profile. This proves that the IP settings were provided by the Radius server as part of the access accept message. We can use the show Radius server command to list all Radius servers including their status. If we add the server name to this command, we get a packet statistic and we can confirm that Radius packets were sent and received. The show Radius profile command summarizes the profile configuration and also shows some default parameters such as the algorithm. Once again, I have created an overview slide summarizing all the CLI commands related to Radius configuration that I have just demonstrated. If you want to try out the examples given here yourself, you will need a Radius server in your setup. We use a free Radius 3.0 implementation running on a Ubuntu server, which requires 2 configuration files, which are shown here as kind of reference. On the left-hand side you will find the user's file, which defines the subscribers. An entry begins with the username, which in our case essentially corresponds to the MAC address, and the password, which is always set to IPoE. Then the different parameters are defined that are returned to the BNG when an access request is accepted. As you can see from the second entry, regular expressions are also allowed if you do not want to maintain a separate entry for each individual subscriber. On the right side you will find the clients.conf file, which contains all Radius clients. The IP address 0.0.0.0 implies that all IP addresses are accepted as the source address of a Radius access request message. Before we conclude this section, we would like to briefly mention that RBFS offers options to adjust the accounting data in both directions. This is useful to normalized accounting counters that result from different encapsulation types. The byte adjustment value supports positive and negative values depending if you want to add or subtract bytes. I hope you enjoyed this clip on configuring IPoE subscriber management in RBFS and will see you again soon for the next one. Thanks for your attention.